Welcome everyone to the second day of the workshop of Math AMSud. And it's a pleasure to introduce the first speaker of the day. It's Hamid Hassanzadeh, and he's going to talk to us about a genus explanation of Buchsbaum-Rim multiplicity. So when you are right, you can start, Hamid.
Okay. Thank you very much, Luciani. And let me first thank the organizer and the administrators of this Math AmSud program. It is very nice. I think I had already an experience to do this in 2015, and I'm very happy to participate again in this event with you. Okay, so today my talk is, I would say, is more algebraic one. So as we are going to talk about the algebraic aspect of this geometric object. So my talk is a little bit technical and it has several details. So I managed to not to talk so technical thing, because then the main audience cannot follow me. So instead, I will talk more about introductory and the history and the philosophy that this, in fact, that created this work. So this is a genus explanation of Buchsbaum-Rim multiplicity. So there are many words. Maybe Buchsbaum-Rim multiplicity is already a strange name here, but soon you will see that it is a very good thing. And this is a joint work with Vinicius Bussa, Tiago Fiol, and Jose Naeli. Okay. So as you see, I'm going to talk about multiplicity theory. So multiplicity theory is one of the classical invariance topics in commutative algebra and algebraic geometry. Maybe the very first definition of multiplicity comes after the Hilbert theorem, to define the Hilbert multiplicity. So let me just recall very basic definition of the Hilbert multiplicity. So let R be a graded ring or an Artinian ring and of dimension D. Then Hilbert shows that the function Fi, which is length of Ri as an R0 module, so this function is eventually a polynomial. And then this polynomial is called the Hilbert polynomial of this ring. And the polynomial is a function, is of the form E, d minus 1 factorial, I to the d minus 1 plus blah, blah, blah. And this number E here is called the multiplicity of the ring R, or the Hilbert multiplicity of the ring R. I imagine that everybody knows this definition. So this definition of Hilbert that works for the graded ring, generalized by Samuel, so this was Hilbert, and then Samuel generalized this for local rings. So you take a local ring, so a local Noetherian ring, and you take an ideal of definition, so it means an ideal whose radical is just the maximal ideal. So again, Samuel shows that the function Fi, which is the length of R over powers of Q as an R module. So again, this function is a polynomial function for big enough indices I, and this polynomial function again is of the form, now it is of the form D factorial I to the D. So this is a polynomial of degree D, and this coefficient here, numerator of this fraction here, which is EQR. So this is called the Samuel multiplicity of R with respect to the defining ideal, to the ideal of definition Q. Okay. So then, of course, in the case that this is a local ring, then these two become the same. And so then the Hilbert-Samuel multiplicity, so the theory started from this point, has a very significant role in the study of singularities, and especially isolated singularities, okay? Because this is a local property. So then you measure how singularities are singular, how singular of the singularity. Okay, but the history continues. This is, this part is very prehistorical, but the history continues after Hironaka's resolution of singularity. So when he settled the question of resolution of singularity in 1964, so then the attention from resolving the singularity changed to classifying the singularity. So after 64, the history became like this, and people were interested to understand what type of singularity that variety has and so on. So so when you talk about type of singularity, so a very natural thing is to understand when the singularities are the same, where there are some equivalence between singularities. And it was a notation that introduced by Zariski. So in 64, maybe, or between 64 and 79, so Zariski worked on the concept of equisingularity. Okay, so equisingularity is to study singularity in families. Okay, so the fact is that there are many surfaces that they all have a very similar singularity. So you like this hypersurface here, and you see that all of the singular points are here located in this line here, and then you have curves which this curve constitutes a family, and this family have a very similar singularity. So the idea of equisingularity appeared, and it requests to understand what type of invariant can measure singularities in a family. So how can we say that this singularity are the same, are similar, and how can we consider all as similar singularity? Okay, so then, so the theory of equisingularity was very active in that decade, and one of the major work was done by Gaffney. So then Gaffney tried to find, of course, Tessier also worked on this family, and he defined what is called the mixed multiplicity. But Gaffney also tried, had significant progress in this theory. And so what Gaffney discovered was that to understand the singularity in family, one not only needed to understand the Hilbert-Samuel multiplicity that works indeed for isolated singularity, but also one needs a theory of singularity or a theory of multiplicity for modules. So this was the idea of Gaffney, that to study this family, we need some multiplicity for modules. But what happened was that exactly in 1964, Buchsbaum-Rim had already established this theory of multiplicity for modules that is still bearing their name, and we call them the Buchsbaum-Rim multiplicity. So Buchsbaum-Rim multiplicity is a numerical invariant that we associate to a module, and we call the Buchsbaum-Rim multiplicity of that module. So soon I will define what is Buchsbaum-Rim multiplicity, but until now, what you need to know is that this theory of Buchsbaum-Rim multiplicity is a theory to understand this kind of singularity in families. Okay, now let me take you to another historical part of algebraic geometry, which is intersection theory. So intersection theory, as everyone knows, one of the classical objects in algebraic geometry. But in 1940s, so Andre Weil established a set of like 7 axioms that any intersection theory must satisfy. To be any good intersection theory, okay, must satisfy those axioms. And nowadays we know that this, the intersection theory contains 2 main ingredients. One of them is the Chow moving lemma. And the other is the correct definition. So every board here has a history, but okay, the correct definition of local intersection multiplicity. So these two things are the main ingredient of the nowadays intersection theory. And this second one, established by Serre in 1958, and he defined the local intersection multiplicity, and he showed that this is the correct definition, because before that there were other definitions that were not satisfactory considering the axioms. So, to define the Serre's definition of local intersection multiplicity, so let X be a regular scheme. So you can take any smooth variety if you wish. And let Y and Z be 2 closed subschemes of X that intersect properly and let W be an irreducible component of Y intersections. Okay, then Serre defined the local intersection multiplicity of Y and Z in W to be the alternative sum of lengths of Tor I, A over A, and A over B, where this A is the local ring of W in a generic point, in its generic point, and A and B are ideals of Y and Z in A. Okay. So this was the original definition of Serre, and Serre showed that this number is what we understand as the local intersection multiplicity of the variety Y and Z in the component W. So this is very non-trivial to show that this is indeed the intersection theory that we need. But of course, Serre did that in 58. And the very first thing to show that this is a good theory is to show that at least this number is a positive number, is a non-negative number, right? So the intersection we do not expect to be negative. Yeah, at least the. Okay, so one has to prove at the beginning that this is a positive number. So to prove this positivity, what Serre did, so he used the method of reduction to diagonals. So to do this reduction of diagonal, he introduced the complete tensor product. And so he reduced the case of studying this Tor I and I over A and A over B to the case that this A is generated by a regular sequence. So he reduces to the case that A is generated by a regular sequence. So what is the benefit of having a regular sequence is that then the causal complex of X over A becomes the minimal, so this becomes the minimal resolution, minimal free resolution of A over A. So at least, you know, to compute Tor, you need to take a minimal field resolution of one component, tensor into the other component, and calculate the homologies, right? But if this is a regular sequence, then one of these necessity is very easily satisfied, and then we have the structure of the Kuzul complex as a resolution, and then Tor I A over B is just the ith homology of the Kuzul complex with respect to these R elements, so KR, K0, tensor to A over B, right? So if you do this, then you have this Tor, but when you compute this homology, so you take the Kuzul complex, tensor into AB, calculate the homology, so you are computing the Kuzul homologies, not just the Tor modules. So then this is just the homology of Kuzul of F's for AB. And I said these varieties intersect properly, so this F is an ideal of definition for AB. It's a system of parameters indeed for AB. So these guys are all of finite length, and then you can calculate the length of this. So then the problem of computing the local intersection multiplicity, so become equal to computing this alternative length of the Kuzul complex as an A module, right? So what Serre did next, so in another celebrated theorem, so he showed that this ladder, so the alternative sum, so Serre showed that this alternative sum is indeed the multiplicity of F and A over B. So the Hilbert-Sumwell multiplicity with respect to F over AB, and we know that the Hilbert-Sumwell multiplicity is a positive number. That's it. Okay. So, I mean, there are many details in this proof. It is all in the book of Serre, local rings, in the chapter 4 and 5, but then there are many details that one still has to check. But what I'm now going to concentrate, to focus, is this formula of Serre. So to understand what is called nowadays the Euler characteristic of the Kuzul complex. Okay. So let me now go back again to Buchsbaum-Rim multiplicity. So as I said, Buchsbaum-Rim multiplicity is a vast generalization of Hilbert-Sumwell multiplicity. But this formula of Serre was really fundamental in developing the intersection theory in this sense. So if one would like to generalize the Buchsbaum-Rim multiplicity and another theory of intersection theory, one need to understand an explanation of the Buchsbaum-Rim multiplicity in terms of the Kuzul homologies, right? And this is what I'm going to talk about. So what would be an explanation? So a question is that, what is an explanation of Buchsbaum-Rim multiplicity in terms of Kuzul homologies? Okay, so this is the motivation of this talk and this paper that we work on, and I'm going to answer this question today. So of course, this is a very natural question, and everybody, especially Buchsbaum and Rim, since the creation of the Buchsbaum-Rim multiplicity, they were aware of this question and they tried to answer this question. But the point is that there is no ordinary Kuzul homology that indeed can satisfy the exact form of the Buchsbaum of the Serre formula, because then in higher dimension, these homology modules are not necessarily of finite length, and then one has lots of difficulties to handle them. So what Buchsbaum-Rim did was that they modified Kusul complex, right? So instead of working with Kusul complex, they created another type of complex that are reminiscent of the Kusul complex, but not the Kusul complex, had many properties such as Kusul complex has, but not exactly what Kusul complex served as a resolution or free approximation, right? So at the end, I think it's now time for me to write some mathematical thing here, to write some formula, no? Okay, let's just stop 1 minute and ask for a question, and if there is any question or things to discuss here or not. So in this historical part, do you have any questions? Okay, and then I hope now everyone has the idea of the motivation of this talk. Okay, so we are going to explain Buchsbaum-Rim multiplicity as the most similar way to the explanation of the Hilbert-Samuel multiplicity in terms of Kusul homology, so ordinary Kusul complex. Okay, so let me recall definition of Kusul. I hope everybody knows that, but just to be sure. So Kusul complex for R elements in a ring A is just the differential graded algebra of the exterior power A of the exterior algebra AR. So it means that so it is a complex that defined from with differentials from IR, the exterior I to exterior I minus 1 of AR, and it sends U, let's say U1 EI to the sum minus 1 to the J, and then you take Fj, and then you set E1, and then AMID EJ to each. Okay, so this is the definition of the Kusul complex. And well, that's it. But the question of Buchsbaum-Rim multiplicity is more complicated, because then you don't have a single row, but you have a matrix. So if you have a matrix, so the setting is like that. So then you have your module M, and you have a presentation for this module. Say, well, I will write R or A. I don't know. I don't care, because R for me is just a Noetherian local ring, is very general. Okay. So then you have a presentation matrix for this. So I set this matrix with C11, C1F, CG1, CGF, right? So we assume that F is bigger than G for some technical reason. So then, what Buchsbaum-Rim did, they tried to generalize the concept of Kusul complex, okay, to another type of complex that can encompass all of the property that we expect from Kusul complex. And this family of complex is nowadays called the Buchsbaum-Rim complex. Okay, so it is like denoted by B of this matrix, say phi. Okay, so what is the Buchsbaum-Rim complex? I don't like to explain the details, the details of this definition, but just to simplify, Buchsbaum-Rim complex is a combination of G Kusul complex. So for any row of this matrix here, you can write a Kusul complex. Okay, and then in a clever way, you combine these G complexes, and then you generate a bigger complex, which is called the Buchsbaum-Rim complex. Okay, so what Buchsbaum-Rim showed, they showed that if you work with this complex, if you assume that this module M has finite lengths, and then you work with this complex has a very similar property as Kuzel complex. And then they show that if you work with this, then the Euler characteristic of this complex, which by definition is the sum of the lengths of the of the homology of this complex, right? So then the Euler characteristic of this complex is exactly the Buchsbaum-Rim multiplicity of the module M. Okay, good. This is indeed what one would expect, no? Because then they indeed generalize the set result for Buchsbaum-Rim complex. But the only bad thing is that here, this complex is not indeed a Kuzel complex. It is a generalization of Kuzel complex, and this is the Buchsbaum-Rim complex, right? But anyway, this question remained for since then. So everybody thought that, okay, to work with Buchsbaum-Rim multiplicity, we have to use Buchsbaum-Rim complex instead of Kuzel complex, right? But here we want to show that not necessary. We can still go back to the ordinary Kuzel complex and again obtain the Buchsbaum-Rim formula. Okay, so again, this complex of Buchsbaum-Rim attracted attentions, and people try to understand other generalization of Kuzel complex. So when Kuzel can be generalized to Buchsbaum-Rim complex, so there are many natural ideas to generalize still this generalization. So that Kirby in 85 and Buchsbaum and Eisenbach almost the same time. So they generalized the family of the Buchsbaum-Rim complex to a family of complexes which nowadays are called or generalized Kuzel complex or Buchsbaum-Eisenbach family of complexes. So they define a parameter T, and for any parameter, let's say V, and then for any parameter V, they define a new complex, and every complex has a nice property, okay? So, so in particular, Kirby showed that all of this family of complexes, if you look at the Euler characteristic, they will provide the Buchsbaum-Rim multiplicity. Okay, not bad. So we want to explain Buchsbaum-Rim multiplicity in terms of Kuzel complex. We couldn't explain by Kuzel complex, we generate another complex, and then we generate many complexes whose Euler characteristic define the Buchsbaum-Rim complex, but still one look for the Kuzel complex, right? Okay, now let me go, and now still a little bit technical thing to state at least the main theorem of our work, okay? So let me just define for you what is the Buchsbaum-Rim multiplicity. Now, it's a shame if I talk about Buchsbaum-Rim multiplicity and that I do not define the Buchsbaum-Rim multiplicity. Okay, so so again, we have a module. So module is nothing but a matrix. So then C11, C1F, CG1, CGF, right? And then you should look at the symmetric algebra of this guy. Symmetric algebra is a quotient of the polynomial extension of R. So R extended by new variables T1, Tg, divided by equations of M comes from CG. So it is a set gamma 1, gamma F. And this gamma 1, gamma F is just the product of the matrix T1, Tg to the matrix C11, C1F, CG1, CGF. Okay, so just gamma 1 is T1, C11 plus T2, C21 plus Tg, CG1, and so on. Okay, so you have these equations here, and then you have the symmetric algebra here. Good. But the notation here, of course, blew up. Everybody knows what blew up is the Riesz algebra. And then if you wish to understand what would be a theory for Riesz algebra of module, then Riesz algebra is the algebra generated by these forms, gamma 1, gamma f, in the polynomial ring S, which is R T1, T2. Okay, so this is the Riesz algebra of module, and we have this polynomial extension, which is indeed the symmetric algebra of this free module. Okay, but then what Buchsbaum and Rim showed, they showed that, so Buchsbaum and Rim 64, they show that if length of M is finite, then the function Fi, which is length of S is this polynomial extension over R gamma 1, gamma F. Okay, gamma 1, gamma F is just the equation of the symmetric algebra. If you look at this guy in degree I, then they show that this guy has finite length, and then this function that defines the finite length, okay, this is a polynomial. So in the case that you have only one, F is 1, then you recover the ordinary Hilbert-Sumwell multiplicity or just Hilbert function. But then this definition allows to go further and consider symmetric algebra, a Riesz algebra of module instead of Riesz algebra of an ideal. Okay, so then this function become polynomial, okay, for big and of degree BR, of the form BRM, D minus plus G minus 1, where D is dimension of R, I to the factorial, D plus G minus 1, and so on. Okay, so this coefficient here is the Buchsbaum-Rim multiplicity. So just let me recall once more, not to forget the notations. So we have a module M, we have a matrix here. These are the entries of the matrix. We take new variables T1, Tg, we multiply them into this matrix to obtain the symmetric algebra equation. So these are just the linear syzygies. Okay, then we consider the algebra generated by these things. This is the Riesz module, the Riesz algebra of the module. And then you look at the I component of this quotient. So S was R of T's, okay, the new variable. And here we have R of gammas that are the linear syzygies. So if you look at the I's component, this is a function for I big enough, and this is a polynomial for big enough, and of the form this, and this coefficient is called the Buchsbaum-Rim multiplicity. Okay. Okay. So I would say that we want to explain this guy in terms of Kuzel homology. So what would be the candidate of Kuzel complex? So we consider Kuzel complex K of gamma itself. Of course, nothing is more natural than gammas. Okay, so we have this linear syzygies. So again, gamma. So you have the presentation matrix. You multiply into TIs, and you have this gammas. Okay, so you look at this Kuzel complex of gammas, and you look at the homology of this Kuzel complex. Okay. Even though module M is of finite length, these homologies are not of finite length, right? But still, we would like to explain Buchsbaum-Rim multiplicity in terms of the disordinary Kuzel homologies. So instead of looking at the length of the whole thing, we look at the length of the components. And then the main theorem is the following. Okay. So we prove the following. Let R and M be a Noetherian local ring. let M be a finitely generated module of finite lengths, and let PHI be the Hilbert polynomial of the homology module HI. So HI is the homology of the Kuzel of the linear syzygies equations. So look at the Kuzel homology, the Hilbert polynomial of Kuzel homologies. Okay. Then, of course, here we have a natural grading. So when you look at S, you have R of T1, Tg. Then we set this guy in degree 0 and this guy in degree 1. Okay. Okay, then we show that for any integer v, the alternative sum of the Kuzel of the Hilbert polynomial define the Buchsbaum-Rim multiplicity. So this is true for any v. So okay, so I think this is an explanation of Buchsbaum-Rim multiplicity in terms of the Kuzel homology. So, but look at that. This is not a very complicated formula. This is just the Hilbert, the ordinary Kuzel complex, HI, right? And then this is true for any v. The best v maybe is when v is 0. And then you have the constant element in the Hilbert polynomial for each HI. So if by abusing notation, I call this constant the arithmetic genus, okay, and between quotations. So then our explanation of Buchsbaum-Rim multiplicity is the following: is the alternative sum of arithmetic genus of HI is just the Buchsbaum-Rim multiplicity, right? Okay, so this is the main theorem that I want to talk. So I from 0 to G. So as I said, so this is a new theorem, and the method we applied does not use the SER, none of the SER argument. This is completely independent of SER argument. So in particular case, when G is 1, this arithmetic genus becomes the length, okay? So this is a new viewpoint to the length of a module. In higher dimension, you can imagine if it is the arithmetic genus. So then Buchsbaum-Rim multiplicity is the alternative sum of the arithmetic genus of the Kuzel homologies. I think this is a good explanation and can open the way to go through the intersection theory from this point on. Okay, so I think I have like 7 minutes, right, Lucian?
Well, yeah, maybe Hamid, you would like to have questions too. So if you could.
Yeah, like 2 minutes.
4 minutes is okay.
Okay, okay. Okay, for me is enough. I can just explain a sketch of the proof, right? But of course, the proof has many details, and I avoid them. But just to see that how we could establish this. So it has many steps, and one of the main steps comes from another work of me and Vinicius. So in 2019, we show that the family of Buchsbaum-Rim, Buchsbaum-Eisenbach complex or generalized Kuzel complex, they can all simply constructed from a Kuzel check spectral sequence. Okay, so one take the Kuzel of this form and you tensor this into the check with respect to the variables, and then you have two spectra, the horizontal and the vertical spectra come from this double complex, and these two spectrals, there are some tricky things that you can join the horizontal spectral to the vertical spectral by some transcoloration map, and every piece here can construct another family. And we saw that all of these the family of Buchsbaum-Rim and the Buchsbaum-Rim, Egan-Norskott, Buchsbaum-Eisenbach, Kirby, all of these are just a strand of this Kuzul-Check spectral sequence. This is a very unified explanation of this whole family of complexes. So this was very essential for us. But then we show that in the case that the length is finite, although the Kuzul homologies are not of finite length, but if you look at the sheaf, the sheafification of these modules, okay, so if you look at the sheafification of Kuzul complex, Kuzul homologies, then all of the sheaf cohomologies of these sheaves, twisted sheaf cohomologies, all of these are finite lengths. Okay, for any Q, for any V, and for any P. Okay, so then one goes on and consider these finite length things, and then we show that the alternative sum of this thing is indeed the Hilbert polynomial of P, of HP. Note that here R, so you look, X is the projective scheme over a spec of R. It is not over a field. So this theory is not exactly the classical theory of Hilbert polynomial. So we have to work on a Noetherian ring instead of a field. But even though we can, reduce to that case, and then we take back the polynomial structure of the Kuzul homology. Anyway, so this was crucial, and then finally we use a result of Kirby that shows that the Euler characteristic of this family of complexes is indeed the Buchsbaum-Rim multiplicity. Okay, thank you for your attention. I will stop here.
Thank you, Hamid, for the nice talk. Let's just, and someone has questions, comments? Hopi? Yeah. Hopi?
Sorry, I was clapping.
Okay. Okay, sorry. Yeah. So somebody has any question or comment? Well, so let's just thank the speaker again. And